All right. Dimitri, for you, I fixed the picture so it's very clear.
Okay. Thank you.
Yeah.
I can see those.
Okay, I want to start with a little demonstration. So can I have 3 people of reasonable balancing skills, people who think they're good at this, come on up. Okay, Dimitri. I don't know why I say Dimitri today. Dimitri
You can
James,
say Dimitri.
Ryan. Okay, we have one more.
It makes us feel nice and proper.
Okay, come on up, Michael. Okay, so each person gets one of these things.
I call me stick. I'll take the next longest stick.
Okay, so here's what we're going to do. Spread out so you don't run into each other. We're going to have the 3 of them balance it on the end of their fingertip. And the one that can go, like this. And the one that can go the longest wins.
Oh, here we go.
Sorry. The end.
Okay, so, the long way.
Yeah. Okay, so we ready? And if we go past the end, we'll just call it. Okay, go.
You just stop.
Okay.
A minute or what?
So, yeah. Why? Let's shuffle it up. Let's reverse it now. DJ gets the same one.
Okay. Just second time return.
So we'll try again now. So ready?
Okay.
Go. Okay. This time none of them was very long, bro. But in each case, the winner was the meter stick, and the loser was the marker. I switched it up so you wouldn't think that it's a coordination issue here. Thank you, gentlemen. Okay, so what we saw was this one here, you can balance probably until you get bored, right? This one's really easy to balance. Whereas this one here, God bless you if you can go for more than 2 seconds with this one. Why is this one so much harder to do than this one? Okay, Ryan tried to think a few things and said he had no idea. I appreciate that. Anybody have any idea?
The differences in the force are so drastic whenever it's closer than when it's up there.
Okay, something to do with when it's up there versus close. So if this starts to fall, what does it do? If I keep my finger in one place and starts to fall, what does it do?
The weight?
Okay, it starts rotating, right? When the weight is not over my fingertip, it will start rotating. Why is it rotating? What is the physics term for why it rotates? What is a thing that makes it rotate?
Perfectly aligned, so gravity's tilting it.
So gravity is creating there's a certain word, a torque. Gravity's creating a torque. And that torque is, of course, going to be the perpendicular distance to the force times the force. So the center mass on this is probably around here, right? That's about, okay, there should be the center. And so when it's tilted like this, the perpendicular distance, okay, this is the radius arm, right? But the perpendicular distance, since the force is vertical, is just this distance. So that's how we get the torque. When this tilts, there's a torque. When this tilts, there's a torque. Which torque is going to be bigger, by the way? Because this one's bigger because assume
acted over a greater distance.
The perpendicular distance is going to be longer. Okay, so this one's going to have bigger torques, yet I can balance it easier. How does a torque affect motion? We have Newton's second law for forces. How did a force affect motion? Somebody just quote from me Newton's second law. Okay, some of the forces is mass times acceleration, or in terms of momentum, we had the sum of the forces is equal to change in momentum over change in time. Now, if we go to rotation, what's the rotational equivalent of that? L is the angular momentum over change in time. Or Just like here, we would have had equals MA. So I should have put the MA form because it is the I alpha form I want. What is fundamentally different about this compared to, well, this is a different one, but this? The length. And so the moment of inertia is going to be the distance from here to where each piece of mass is. And, for a rod, it comes out to be, what? M length squared times 2/3, I think it was. We'd have to look at the table because I don't remember, and I'm not going to do the integral right now. But it's proportional to the length the moment of inertia is. Proportional to the length squared, in fact. So if I double the length, the moment of inertia is going to be 4 times bigger. And notice we have the change I times alpha. So if we have the same torque, if I is 4 times bigger, what's alpha going to be? It's going to be 1/4 the size, 4 times smaller, which sounds really awkward to me. So I say 1/4 the size. So it's going to have a much smaller angular acceleration if I have a larger moment of inertia. Now the torque is bigger, the torque is double. But the moment of inertia is 2 times 2, 4 times bigger. So the net result is, if you double the length, the ratio of the moment of inertia to torque is twice as big, which means that the angular acceleration for the same object is going to be half as big. Smaller angular acceleration means in a given amount of time, it does half of the change in angular velocity. You have more time to correct. So the key output of all of this, right? I went through it in long, nitty-gritty detail. But the key output is, if you have the longer object, it has a larger moment of inertia, and you have more time to correct. So you can make your corrections very quickly compared to how quickly it falls, and you can just keep balancing it. So this Sabbath, we were walking the railroad tracks. This is what reminded me. And if you put your hands out, it's easier. Why is it easier with your hands out?
More time for correction.
You have more time for correction. With your hands out, you raise your moment of inertia, right? They're farther away from the pivot point, which is your feet, when they're out here than when they're here. So you're raising your moment of inertia, hence you have more time for correction. So if you watch, high wire acrobats, sometimes they're walking with this big bar. They're walking with that big bar because it has a really big moment of inertia. And so if they start to lose their balance, they're going to really go slow as they fall. They have plenty of time to get back in balance. And so, if you're just walking by yourself, you actually have to be not paying attention to fall if you have that big bar. Now, if you're doing some crazy stunt where the flying Walendas having their big pyramid, well, there's a reason they held these, even though they ended up killing half the family. I don't know. We watched that movie when I was a kid, and it scarred me for life. So I just wanted to go through something that we've done in the recent past, make sure we understand how that plays out in real life scenarios. Okay, we ended last class period by looking at this picture of one young lady auscultating the blood pressure of another. And, well, actually, is she auscultating? No, she doesn't have a stethoscope, does she? No. Well, she's probably not palpating either. She probably just has a machine that's doing it for her. But how many people know how to take a blood pressure? Okay, so we have a lot of people. And everybody's had their blood pressure taken. And sometimes you don't know what's going on, so just to make sure we know what's going on, you put the cuff in the arm, and then you fill it up with air. As you fill it up with air, the pressure, of course, inside of that cuff is getting bigger, and it's transmitting that pressure into the arm. And so you're putting that pressure on arteries going through the arm. And, well, you put it on the veins too, but you know what? The veins are easy to collapse. So as you push on the arteries, if you push with a high enough pressure, you can squeeze the artery shut. And when the artery is squeezed shut, you have no sound. When the artery then is opened up a little bit, you hear the squirting of blood going through that almost closed artery. So when they're measuring the blood pressure, first they have to raise the pressure enough so there's no sound. There's no blood getting through. That's why it's kind of painful, because you're not getting blood to your hand. And then they lower the pressure until you're not quite collapsing that artery when you have the heart pushing, when the heart muscle is contracting the systole or the systolic part of the heartbeat. And so when they hear that squirting sound, then they know we now have the pressure on the cuff matching the highest pressure that the heart is producing. And then they lower the pressure some more until the squirting stops. At that point, they're no longer constricting the artery and the blood is flowing freely, and that tells them what the blood pressure is going to be just when the heart's not pumping and blood's going through. What we call the diastolic pressure, diastole, I suppose. They don't measure the asystolic blood pressure, because what is asystole?
Death.
Asystole is the heart's not pumping. You don't measure that. So that's what's going on. That's the whole idea with the cuff and what you're listening for. So when you're auscultating, that means you're sitting there and you're listening for it. You could also palpate. You use your fingers and you feel no pulse, means no blood coming through. You open up a little bit and you start feeling the pulse, and then you know what the systolic blood pressure is. So palpation, at least the way I learned it, we only get the systolic. We don't get a diastolic from palpation. And we won't go any further with that. The picture is actually here because it's just illustrating the types of things that are used to measure the pressure. That is the anemometer, I think was the name for this one. I took the names out. Or a manometer. A sphygmomanometer actually is the name for, aneroid sphygmomanometer for this beast. All right. I started last class where we talked about Archimedes' principle. DJ got me all flustered. Now let's get to Archimedes' principle. So we all have the story of Archimedes in our heads. What is the way Archimedes' principle actually works? Remember, what we talked about yesterday for Archimedes' principle was when you get in water, you displace water. And what Archimedes actually realized was that if you float, then the weight, you displaced water. You moved water out of the way. And the weight of the water that you moved out of the way is going to be equal to the weight of the thing that's floating. So if something floats, you're going to have the displaced water equals the weight of the thing floating. If it sinks, the displaced water is still going to be equal to the net upward force on the object due to water. Now, go back a couple days in lecture, and we talked about the pressure being higher as you go down lower. Because the pressure is higher down lower, there's more upward force than downward force. So this picture here shows a cylinder. This is supposed to be a cylinder of water, and it takes that cylinder of water, cuts it out, and puts it outside for us to analyze. So it's supposed to be the same cylinder of water. It's made a cylinder because it just makes thinking about it easier. What direction is the force due to water pressure on the sides of the cylinder? Force and pressure always point to what direction? Okay, into the surface. Normal into the surface. So on the sides, the force is pushing in. But because of the symmetry here, for every point on this side, there's a point on this side that's exactly equal and opposite. So the net force in the horizontal direction is going to add up to 0. You can see that pretty readily using the cylinder as your object. It doesn't matter what shape you use, you're going to still have that result. It's just easiest to see with the cylinder. Now the top has a downward force, that's the water pressure on top times the area of the top. The bottom has an upward force, that's the water pressure at the bottom times the area of the bottom. And so that's what is shown in this picture, the downward force, pressure on the top times the area. Upward force, pressure on the bottom times the area. And then, of course, there's the weight, mg. So this is showing all of the forces acting on that cylinder of water. And what we do is we say, well, if I want to apply Newton's second law the sum of the forces in the vertical direction is the upward force. There's my upward force, pressure 2 times area, minus the 2 downward forces. There's one. Here's another. Now, that doesn't look like mg, right? That's not mg. But it really is, because mass is density times volume. And for a cylinder, volume is equal to the area times the height, which in this case we use the letter D for. You can see right there. And so you put that in, and you get mass is density times area times D. So the net force on this object is pressure at the bottom times area minus pressure at the top times area minus density times area times the height difference times G. Well, how does this help us? First, we give a name to this right here. The pressure, the force caused by the pressure difference, we call the buoyant force. The force buoyant. And how do I calculate the pressure difference? If I have a height difference of D, what's the pressure difference? I don't have a slide with it today, but we've talked about this numerous times. You did a problem at the end of class using this equation. What's that relation for pressure difference with depth?
Density, weight of gravity, height.
It's
Okay.
pressure atmosphere plus.
Okay, I'm looking for the difference, so that's why we dropped that off. You're right in thinking that. But for the difference, it's what DJ said, the density times the acceleration of gravity times the depth. So that's the difference in pressure. And so the force buoyant is density. Now, what is this the density of?
Water.
Water. In this picture, it didn't matter which one because my cylinder was made out of water, right? Hence, this had to be 0 because it's in equilibrium. But this is always going to be the density of the fluid. So if I have something that's not water that I dangle in the water, I'm going to have the buoyant force is the density of the water times the area times the depth times G. But once again, I'm changing colors just because I get tired of using the same one. Since area times D for my cylinder is volume, the buoyant force is density of the fluid times G times the volume of my object. Now, this is not a perfect proof. That is, it's proof for one case. I would have to go through and do the same thing for every single geometry if this was the way we, set up this law. It's set up more generally, doing more sophisticated calculations, but it turns out that this is always true. The buoyant force on an object is equal to the density of the fluid displaced times the acceleration of gravity times the volume. And if the object is completely underwater or under the fluid, that's going to be the volume of the object. If it's not completely submerged, then it will be the volume displaced. So in general, we'll put volume displaced. Okay, I'm going to just put force buoyant over here. The volume displaced, so that if it's completely submerged, volume displaced is volume of the object. If it's not, well, you have to determine it. And now we come to, now that we have this, and this is the important equation, we're going to be studying this equation in lab tomorrow, I believe. I think. Now we get to Archimedes' principle and how it related to that crown. So with the crown, if the crown completely sinks, then the volume displaced is equal to the volume of the crown. And so the water displaced is going to be equal to, in volume, to the volume of the crown. So you measure that water displaced, and of course, that water displaced is going to have volume displaced. And if I take volume times the density of the water, that gives me the mass displaced. And mass times G is force, specifically the weight. So the weight of that water displaced is equal to the buoyant force. So that's a really important outcome for how we use this in a practical sense. If I have, let's say I want to find how much volume James has. I take James and I have a pool. I measure very carefully what the volume of the pool is. And then I have James get in the water, make sure he's underwater, and measure what the volume of the pool is now. Measuring the difference in that volume tells me what James's volume is. And then once I know James's volume, I can find his density by having him step on a scale, measuring his weight, divided by G, that gives me the mass, and then divide by the volume. We usually do this in a simpler method. Why do we do things like this? Has anybody ever done something like this? No? We usually do something like this to measure percent body fat. Because fat is low density, muscle, organs, bone, higher density. And so by measuring your body's overall density using series formula, you can calculate what the percent body fat is reasonably accurately. So you have a person get in the water and you have them like hold a jug and you measure how much air you have to put in the jug for them to float, assuming they sank. And then once you do that, you can once again calculate all of these numbers. So the whole point is to find the density of the person in that case. So what are the important outcomes here? The very important outcomes are, number one, knowing what the buoyant force is. The buoyant force is the net upward force caused by pressure increasing with depth. Number two, being able to calculate what the buoyant force is. The force buoyant is the density of the fluid times G times the volume displaced. And then number three is knowing that the weight of the displaced fluid is equal to the buoyant force. Those are the three important things to get from this. Now, before I leave this, I want to talk about floating. Why do things float? There's a lot of different answers you can give that are correct. So,
They have a lower density.
okay, they have a lower density. Well, why would having a lower density matter? If something floats, it means its net force is zero. It's downward. So that means that the buoyant force, the density of the fluid times G times the volume displaced, is going to be equal to the downward force, which is the density of the object, times G times the volume of the object. Now notice those were two different things, object and fluid. So if something is a floating object, sum of the forces in the y direction is equal to 0, is equal to the force buoyant minus the force of gravity, is equal to density of the fluid times G times the volume displaced minus the density of the object times G times the volume of the object. Now we have a limiting case. Actually, let me solve this for density of the object. If something floats, the volume displaced by definition is less than the volume of the object because part of it is above the fluid level, not displacing anything. So if something floats, that thing in parentheses has to be smaller than 1, which then means the density of the object has to be smaller than the density of the fluid. And so the answer that was given by Trace was perfect. We can show here from our equations that for something to float, it has to have a lower density than the fluid. So that's the ultimate answer I was looking for. I won't go for other answers. He'll accept it. If something sinks, what does that tell you about the buoyant force?
It's less than the weight of...
The buoyant force is less than the weight of the object. And if it sinks, the volume displaced and the volume of the object are going to be the same, right? But this equation won't be correct because the sum of the forces isn't zero in that case. In the case of something sinking, the force of gravity is bigger than the buoyant force. And so if you go through and do the same calculation, putting in something that is negative instead of zero, you find then that the density of the object is greater than the density of the fluid for it to sink. So things to remember in contrasting floating versus sinking. Floating, the density of the object is less than the density of the fluid, and the volume displaced is less than the volume of the object. Sinking, the density of the object is greater than the density of the fluid, and the volume displaced is equal to the volume of the object. Now I can go with one more thing. I know I don't have a slide on this, but floating your boat. Boats are made out of iron. How does iron compare in density to water? It's more dense. Now I said boats. Some boats are made out of other things, but we're going with iron here. There's the concrete boat, for instance. That was made out of concrete. There are wooden boats. Whatever. A traditional seagoing ship is made of iron, and iron is more dense. So what should iron do if you put it in water? It should sink. Without thinking, one could then say, ergo, all boats should sink. Nope. All boats are made of iron. False. Okay. Of all the boats made of iron is more dense than water. More dense things sink. Iron should sink. Or boats should sink. Iron boats should sink. It's not correct, though. Why is that incorrect? Because it seems like actually correct logic.
Is the density is the boat, but then the air in the boat.
Right. When we're calculating the density, we're assuming that the thing is, all no air trapped inside. It's just one thing. But the boat essentially is trapping air inside. It's displacing a lot of water, a lot more than it would if you just had iron with water all around it. And so by making it displace more water, you increase the buoyant force, because that buoyant force is proportional to the volume displaced. And so ships are made so they will displace a lot of water, hence get a lot of upward force to counter the weight of all of their cargo in the ship. I know we don't have clickers, but this is a really important question to ask. Which condition is true only when an object floats? Just blurt, A, B, or C?
Just blurt it.
Yeah.
A.
That's a blurt. Now, there were a couple other answers that weren't as loud as Ryan. I do appreciate that, Ryan. I really do. You were wrong? You were wrong because of the word only.
What?
The buoyant force is equal to the weight of fluid displaced is always true, not just only when it floats.
Oh.
So it's a correct statement, but it's not only true if it floats.
Gotcha.
So ruling out A because it's always correct. Okay, so James is getting a little more positive or confident here. B, the buoyant force is equal to the weight of the object. Right. If it's floating, then the net force is zero. And so B is only true if it's floating. Now, the buoyant force is zero. Well, that would be not the right answer in any case. Come on to the next slide. This is just thrown in as a definition. Sometimes you'll see this term specific gravity. Specific gravity means the density divided by the density of pure water at, I have it written there, I don't have to write it down, at 3.98 degrees Celsius. And any reasonable-minded person says, wait a minute, what's so special about 3.98 degrees Celsius? Does anyone have any idea what's special about 3.98 degrees Celsius? No clues?
No. That's when the density of water is the 2009, it's easier to imagine.
That is when water is the most dense. If you raise the temperature, water expands. If you lower the temperature, water expands. It's the most dense there, and that's what we use for definition for, water has a density of 1,000 kilograms per meter cubed. So if you have a different temperature, the density changes just a little bit for water. So that's why that's specific. You know what most people do? Ignore it and say the density of water. The density of water changes just a little as long as you stay in the liquid phase. If you change into the solid phase, and by the way, we should all be real comfortable just saying the solid phase of water is ice, the volume expands, which is really bizarre. Almost everything, the volume contracts when you freeze. The water, it expands. And we'll talk about that later and how that is important for life on Earth. Okay, but right now, just that definition of specific gravity. Specific gravity can be thought of as density in grams per centimeter cubed without showing the units. That'd be another way of doing it. Because the density of water at 3.98 degrees Celsius is 1 gram per centimeter cubed. All right, hydrometer. You guys are all too young for this. Back when I was a kid, we had to put water and stuff in our batteries to maintain the right acidity in the battery acid. I'm guessing none of you had to do that, right? And so when we did that, what you would do is you would measure with a glass hydrometer what the density of your battery acid was. And you would make your determination of, do I need to put more water in or not, based on that density measurement. It's kind of good that you don't do that anymore. I changed my car battery last year wearing these self-same pants. How do I know? Because when I tried to take the post off of the battery, the cable off of the post came out of the battery. And thus, battery acid spilled on my pants, and I have holes in my pants from the battery acid. That's why we don't like to have to change the battery acid. It does what acids do. So the hydrometer, the way it works, you have a glass tube, and inside that tube you have some weight. And so you put that in water, and it will float when the volume displaced is equal to the weight of that object. From the equation that we just worked out on the previous page, by the ratio of the volumes displaced, you can determine what the density of the fluid is. And so you see that this picture here, and I usually bring one out, but I didn't today because I knew I wasn't going to have time to do it. You just have a linear calibration for the depth that it sunk and what the density of the water is. So it's a pretty easy thing to determine density. Now our last fun thing before we get to a problem. Yay! A meniscus. Everybody's seen a meniscus. When I had this out on Friday, we noted that the water level in this narrow one was a little bit higher, like 1 to 2 millimeters higher than the water level in this one, even though Pascal's principle says that they should have been the same height. And so the question is, why? And the answer is surface tension. There's some other questions I could have asked that are equally interesting. Like when I was a kid, we'd go camping out there by 70 fish camp, and I would watch these water striders on the water. How many people watch the water striders on the water?
The bugs?
Yeah.
Okay, yeah.
Okay, it's really, I was always a nerd. I'm looking at that. How does it happen? And then I had to do the experiments. I hope you all did your own experiments. Things like douse it. Clap my hand over, get it underwater, see if it floats back up or what happens. You guys do that?
To the bugs or to your hand?
To the bugs. I know my hand's not going to. Well, you get them underwater and they sink. So why can they stand on the top of the water if they don't float?
Because of the surface tension.
Because of the surface tension. And I'm going to trust DJ actually knew that before me saying this.
I read it.
Yeah, he read it.
No, like
Not here, in the book, in the preparation, okay. They can stay on the water because of surface tension. It's really cool. One of the best demonstrations that I'm not doing is to take like a piece of aluminum foil, or if you're into origami, you make yourself a little paper boat. You float that boat in some water, and then you just put a little drop of laundry detergent or soap detergent in there. Because my EMT teacher got the surfactant idea backward, which is, it's embarrassing when the EMT teacher calls on me to confirm it, and I'm like, no, it's just the opposite. Surfactants are surface acting agents that lower the surface tension. The surface tension is like tension in a string, hence we call it tension. When you have water, there are bonds holding the molecules together. And if you put something on that water, the water's, of course, going to be trying to push them apart, and the water's trying to hold itself together. And so it will put a force, and if you put just a very light thing on the water doesn't want to be broken apart, and it will put an upward force in the object. It puts an upward force because of the force holding the molecules together. By the way, we also call this the surface energy. And so the surface tension puts a force on an object that's equal in magnitude to the length, you see my writing up there, top right, to the length of the contact area times the surface tension, gamma, for the material. So that gamma depends on what the material is, if it's water or mercury or something like that. So when the water strider stands on the water, it has essentially my fist. Fist comes down on the water, and as it sinks, the water then comes up on the sides. So for the water strider, here's its foot, and then the water goes like that. Well, according to the surface tension idea, there's going to be a force, just like when we studied the pulleys. The direction of the force of tension was always parallel to the rope leaving, right? Right. Thank you. So we have the same thing here. We're going to have a force of surface tension that's in the direction in which the water is leaving the water strider's little, I call it a fist. I don't know what to call it. It's landing gear. And so then you have to take the length of contact. Well, the length of contact is going to be a circle with length equals 2 pi r. So it has to do with the size of its little fist there. And then you have to take the upward component, because the sideways components are just going to add up to 0, because you have the symmetry going around circle again. You take the upward component. If I call this angle theta, I'll get the force up due to surface tension is equal to gamma times 2 pi r times sine of theta, so that I'm getting just the upward portion, because the horizontal portions are going to add up to 0. So that tells me how much upward force I can get from surface tension. I actually don't remember what gamma is for water, but very clearly it's not high enough for a human to be able to stand on water and be held up.
Unless you're Jesus.
That's a different principle there. That's a miracle. Science can't. I will take this moment to interject. Science these days starts with a guiding principle that there are no miracles, that everything that occurs naturally. And so science says that's not possible. Whereas as a Christian, I believe in miracles, and I say, yes, there was a miracle. It's a non-natural event. All right, so that's how surface tension works. That's how you can have the water strider stand in the water. You sink it, it goes down. Now, going back to the boat thing, a surfactant lowers the surface tension. If I have a water strider sitting in a little cup and I put soap in the cup, what's going to happen to the water strider? It'll sink because the surface tension drops, doesn't get enough upward force, and down she goes. Okay, so that would be bad. It's much better to do it with the boat. Because in the boat, you have surface tension. Now normally the surface tension in horizontal direction is 0 everywhere. But if I put the soap like behind the boat, it takes time for the soap to diffuse through the water. And so the back part of the boat has the soap first, which means that the water is no longer going to pull back on the back of the boat nearly as strong. So what happens to the boat then? Not just tilts, it goes zooming away because the surface tension on the front is pulling up and forward with now a bigger force than the surface tension on the back was pulling up and backward. And so yes, it will tilt, but it also will take off, which actually will make it funny. And so it's really cool. Of course, people think, no, you just made waves that surf the wave. Well, you can put a drop of water in instead. You have no such action. So a very cool thing you can do on your own. Now, to actually explain what's on here, a meniscus. Menisci is plural of meniscus. So, how does a meniscus work? You have that surface tension, which we also talk about as a surface energy, an energy associated with the molecules together. And then you have a cohesive force that's causing that. You also have adhesive forces, the force between different things. So if I have water and glass, there's a certain adhesive force, the force that's holding the water to the glass. There's cohesive force, the force is holding water molecules together. Now it turns out water likes to touch glass. There's a lower energy when water's touching glass than when water's touching water. And everything in nature goes to its lowest energy state. And so if you have water in glass, you have a lower energy if the water is touching the glass. So water will be pulled to the glass and pushed up on the sides until you reach the lowest possible energy state. And so it climbs the glass. Now, if you look at that picture, it climbs a lot in the center and not much on the outside, but you do see climbing occurring here as well, just much smaller. The reason is the water being pulled up in the center, you have enough surface area available that it pulls up quite a bit compared to how much weight you have to pull up. So that's why you have a rising meniscus. It pulls up, we call it capillarity, and the meniscus is pointing up because the water likes touching glass more than it likes touching water. It has stronger adhesive force to glass than it has cohesive force. Now, if we were to put mercury in the same glass, mercury has a lower adhesive force than its cohesive force. That's mercury likes to touch mercury more than it likes to touch glass. And so for that reason, it will redistribute itself so that it's touching less glass if possible and having a rise up in the center. So that's why you have two different types of menisci. It just depends on which one the fluid likes more, water or glass. For how high it rises, you can actually calculate the total upward force. In this case, for maximum upward force, they measure theta from the opposite direction from I did. It would be 9 degrees using my reference there, 0 degrees using their reference. You have maximum upward force due to surface tension, and that's going to be equal to the weight that you're holding in that column. All right, I think, nope, don't want to do that, don't want to do that, don't want to do that. Want to do this. Our groups, again, so just to remind you, the groups are Wes, Trace, Nathan, Michael, Emily, and Max, Andrew, Sarah, Ha, and Kaylin, Mira, Ryan, and Lydia, Madison, Sarah, Kemp, and Clayton, and DJ, Leslie, and James. You have a question here. A small statue in the shape of a falcon has a weight of 24.1 newtons. The owner of the statue claims it is made of solid gold, which should have this density. When the statue is completely submerged in a container brimful of water, the weight of the water that spills over the edge, 1.25 newtons. Find the density and, well, if you find the density, you know the specific gravity of the metal.
So. So I want to see one disgrace like that.
I need to figure out. So we can easily do this or something. Grab me. We did.
Okay, so we have a group ready to show their solution. I'm actually going to change the application so that you can write. Okay, when this. By the way, today is October 22. Everybody knows what the importance of that is, right?
It's my sister's birthday.
All right.
That's what it was. Apostle Creed is mine.
Yeah. See.
Yikes. We have not teased your birthday.
No, never. Okay. Oh man, I put a bunch of slides in here just in the case. There we go.
So am I writing?
Yes.
Yes. Okay.
Yeah.
Where am I writing this?
You can just slide to the side. Like
Oh,
this.
okay. So to figure out the density, what we first did is we determined the mass of the Falcon. So we took, I don't have the original. Where's my original number here? So we have 24.1 newtons, and to get the mass, we divided that by 9.8. I'm blanking on units.
9.8.
Meters per second. So that will give us 2.46 grams. So that's the mass of the Falcon. What? Kilograms?
Right.
Oops. Yeah.
Is that newtons is kilograms?
That's kilograms, yeah. Oops. And so
This is a lot of gold.
then we did the same thing for the water. So we took 1.25 newtons per second squared, and that gave us 0.6 kilograms. And then we converted that to centimeters cubed by saying 1,000 kilograms over cubed, which is the same. they gave us. Why did they give?
We did it in grams.
Oh, that's why we did it in grams. This is throwing me off.
That would be divided.
Yeah. Okay.
Just throw a divider sign after the G before the parentheses you get.
Oh, just throw it divided.
Oh, yeah. Okay. So that's gonna bring
That's what.
that. Why
Okay.
is this still? Oh, because I still converted that to grams. I'm still like, this is in different units than what I did. Okay, so that's going to give us
1.276 times 10 to the negative.
You know, I'm really just read it. And then we just divided these two numbers. And so we took
What am I getting at? With this calculator stuff.
Yes.
Who's the answer?
It's actually meters cubed, not centimeters.
Okay. Which, if you convert that to be in the same units as what we're working,
That's fine.
That works?
That's a correct set of units.
Nice.
Okay, so is that gold?
Yeah.
pretty, yeah.
Yes.
Yes, it is.
All right, thank you. Have a great Monday. I'll see you in the lab. And yeah,